Welcome back everybody to our playlist on materials informatics. In our previous video, check it out, we talked about Honegumi. Honegumi is an awesome software that we've put together to make Bayesian optimization super simple. In that first video, we walked through our very first tutorial, which was how to optimize a 3D printer to get maximum strength under some constraints. Now let's do another tutorial. In this video, let's talk about how we could optimize a polymer compound for both strength and density. So this is going to be an example of a formulation, right? Optimizing a formulation and doing it for multiple objectives, right? So let's take a look at this in this tutorial. Here's what it says at first. It says, well, by the way, first off, you can click this open in Colab button and it will open it up right here, and you can actually see all the same content here, and you can run it right here in Colab, which is pretty slick. We're going to be doing some of this on our own today, but that's something worth being aware of. Okay, here's what it says. Imagine that you work at a custom materials company, and that company specializes in creating polymer compounds for various applications. Now it says a customer has requested a polymer formulation that has two criteria. They want high strength and they want high biodegradability score, okay? It says the customer is unsure of the trade-off between these two properties, but they know that for any given target application, it's going to have a minimum strength of at least 70 megapascals. So as soon as you hear that, you're thinking, okay, multi-objective, and there's a threshold, right? That we have to be, in this case, above a threshold. It says, as the customer is also concerned about the toxicity and the biodegradability of the polymer, they have limited you to a set of 5 thermoplastic monomers that can be used in the formulation. This is super common, by the way, in the industry. You don't have like this totally blank canvas. Instead, they say, hey, we really want you to work within this system of known chemicals and just find the best one in that system. So here you've got 5 monomers that you're thinking about using. So it says you believe Bayesian optimization can help you with this task, and you decide to put together a script using Honegumi to solve this problem. Again, you can do this on your own. Honegumi is going to make it way easier. So it says, take note, here's your available composition and processing parameters where you're going to try and design, you're going to try and optimize within this design space. First off, you've got 5 monomers, A, B, C, D, E, and these can all exist between 0 and 1, right? So the total composition goes between 0%, 100%, so or 0 and 1. Okay, you have 2 additional parameters, processing parameters. You've got your extrusion rate and you've got your temperature, and these have bounds. The extrusion rate between 0.01 and up to 0.1, and temperature, we're going to say it's between 120 and 200. So it says here, to help you find the solution quickly, you dig up some data on these polymer systems in the literature. Super common to do, right? We look in the literature, we say, well, when other people have looked at these ones, what sort of results have they gotten? In this case, let's say that you're able to find up 3 data points, right? We're going to use this prior information, this training data, as it were, to help us improve our surrogate model by seeing a couple examples, right? Even in cases where these don't do very well, it's important that in some cases it tells you where not to look, right? Okay, so here's your 3 examples. You have 3 data points. Again, here's the 5, 1, 2, 3, 4, 5. That's our monomers. We have 5 different monomers. And then you have extrusion rate, that's X6, and temperature, that's X7. And here you've got some labeled data. You've got labels for strength and biodegradability. And as you can see in this case, none of them actually have sufficient strength, right? Our threshold was it has to be at least 70, and you want, while having at least 70, the best biodegradability score, basically, okay? So obviously in the real world, you would manufacture these things and you would test them. But since we're doing a demonstration here, we're going to have to build a dummy objective function, right? Something that would simulate what the actual experiment might be giving us. So in this case, we've provided one for you. So it's emulating the results of some sort of experimental trial under different inputs. And obviously in the real world, you wouldn't know what this objective function was. You would just measure it in the lab and you'd be trying to learn this. But here for this demonstration, we're going to build this for you. It's a function called polymer properties that takes in our 7 parameters. And then, it's going to do some things. It's going to define what they are. It gives you equations now for strength and biodegradability, okay? So, which are going to be functions of all 7 of these different parameters, okay? And then it's going to return those, okay? In this case, multiplied by 25. In this case, multiplied by 5, okay? So how would you use Honegumi for this? Well, we would hop over to Honegumi, right? And again, if you're landing here and you're thinking about your problem, you think, okay, let's come down to my window and consider all my different conditions for Bayesian optimization. First off, is it single objective or is it multi-objective? Well, we care about both strength and biodegradability. So I'm going to click the button here for multi, okay? Then you're going to say, Is it default or fully Bayesian? We haven't been given information on that just yet, so stay tuned for our next tutorial where we talk about fully Bayesian. Let's just do default for a moment. How about this one? Existing data, false or true? It's going to be true because remember, in this case, we have 3 data points from literature that we're going to use. Even though they're not like, none of them are amazing performers, they're still existing data, which will teach our model something. Okay, the next come are 4 constraints. You have sum constraint, order constraint, linear constraint, composition constraint. That last one is the one we want. And if you didn't remember that, again, you can hover over this cool tooltip and see. It says under composition constraint, choose whether to include a composition constraint over 2 or more optimization variables such that their sum does not exceed a specified total. For example, ensuring that molar fractions add up to 1, which is exactly what we're doing here. So great, we're going to click that one and set it to true. We want a composition constraint. Categorical, in this case, we don't have any categorical features, but we do have a custom threshold, right? Again, we want our strength to be at least 70 megapascals. And then synchrony, we're not told that we're doing things in single versus batch, so we'll leave that as it is. So you could take this exactly as it is right here, and you could hit open in Colab. Let's do it in a new tab. And it's going to take this exact same content here, but it's going to send it over here to Colab, right, where you could actually run it. Okay. Now, this is, if you look at it, this has a default objective called objective 1, which is Brandon, and objective 2, which is Brandon swapped, right? This is a multi-objective Brandon thing. So in other words, this is dummy data right now because this is just the template. But we can take this template, and right here we're going to grab it and copy, and we can jump over here to ChatGPT, and I can say, here is a Bayesian optimization template. Please modify for my specific experiment. Okay, so we're going to drop this template in here, and I'll say, here is my experiment. And then here's where I would describe the exact experiment that was given here in the tutorial. So we come back over here, we can just give it all the same information, right? Let's just actually copy and paste this. After all, since it's a language model, it should be able to populate it correctly, and if not, then we'll fix it, okay? Let's give it everything. Let's even give it the dummy function, right? So we will give it all of that, and we'll come back over here to ChatGPT. We'll dump it in there, and let's see what it's able to do. Okay, so it's finished making the code. It's going to give us a summary of the things that it changed. So it says, okay, from your template, here's the stuff I changed. First off, your objective function, right? It's replaced it with the Polymer properties function that was provided. Great, so now we have a way to simulate our actual test conditions. It says the objective settings, it set a threshold of 70 megapascals. It applied the parameter constraints, ensuring that the different monomer fractions don't exceed 1, and it's provided initial data from those 3 data points. So cool. Okay, so it looks like it's done a pretty good job, but you will want to look over it and make sure that it hasn't made any mistakes. In fact, when I was looking at this, I noticed that there was actually a mistake. If you go back up here and we look at our original training data right here, the compositions for that second data set should have been 00.3.70, but check out what it did. It moved it. It did 0. This is supposed to be 0 right there. That's supposed to be 0.3. That's supposed to be 0.7, that's supposed to be 0. So it is not perfect. It will make some mistakes. So, you know, this is the benefit of language models, that they are incredible. They can make your life much easier, but they do require some supervision and a little bit of skepticism. So you have to catch that error. In fact, if you would have run this, you would have caught an error right here, because if you add those up, that's 0.3 plus 0.7 plus 0.1. It's already over 1. And we imposed a constraint down here, right? Where was it? Here we imposed a parameter composition constraint saying it can't be greater than 1, and yet one of the training data comes greater than 1. So this would have actually thrown an error. So to make our life a little bit simpler, let's go back here, and I'm just going to, in this one, I'm going to open up the notebook, and that, you know, let's use that one because this has the exact same content from this one. Except we've already gone through and we've made sure that the output matches, okay? So we come over here. What's cool is that because you have these links, these collabs, you can edit them directly, and then you can run them straight from the cloud. You don't have to have Python installed on your computer or anything. You do have to get Axe installed, and that will take about 1 minute. Okay, that installed super quick, probably because I was running a notebook just previously. But Okay, so it's got the same content as before. This is the section that would have been copy and pasted from ChatGPT. Let's just make sure that it's done it correctly. Okay, it's got, oh, this is our Polymer, this is our dummy function, right? So this is simulating the experimental results. Okay, we ran that. We've got a dummy function. Here's where we applied the Honegumi with the correct values. Okay, here's where we would have modified our code. Again, this is the part that would have come from ChatGPT. Let's just make sure it did it correctly. See here, you see that second data point is now corrected. Whereas when ChatGPT did it its first try, it got that part wrong, but it usually gets it pretty close. Okay, so it looks like this is ready to run. Let's go ahead and run our optimization and see what we see. Okay, the entire campaign took 5 minutes to run, but we are now finished, right? And it's showing you the progress as you go. Now we have a little bit of extra code that makes it easy to visualize, for example, the parameters. Let's do this one. Let's grab the Pareto optimal parameters. These are going to be the ones that exercise the best trade-off, right? So from this, we're going to use that from the Axe client. And here they are. Here's our trade-off. You can see you've got them ranked by descending strength, right? So you go from your highest strength, 114, 107, 120, all the way down to 79. All of these, by the way, are above our threshold, right? And then you've got them ranked by increasing biodegradability, right? There's a trade-off here. And now you can explore this trade-off between these different parameters. And to make it a little easier for you, you can actually plot them. Here in this code block, we're going to plot them. And we're going to show the 3 data points that we had, all of the data that we collected, the threshold, and the new Pareto front. So here on the y-axis, you've got your biodegradability score. On the x-axis, you've got your strength. The threshold is shown with this vertical dotted line, so any potential solution has to be above that. Here's our 3 data points from historical or literature data, and check it out. Here is our now Pareto optimal solutions. So this is, I think, a really nice example of how you can use Honegumi with a real-world scenario like formulations in the polymer industry with, what was it again? Multiple objectives, compositional constraint, threshold, and prior literature data. In our next example, we're going to explore some of the other conditions that you can work with using Honegumi. Okay, stay tuned.